Hi everyone, my name is Sidi Mohammed Awreed. For my topic, self-driving car, I am presenting a traffic sign recognition using a convolutional neural network. So this is a classification problem. By using a deep learning algorithms. In other words, the problem consists to determine the type of the traffic signs for an input image. So the problem is very challenging for many reasons. So the shape of the image can be deformed based on the perspective, or the image can be affected by the weather conditions, sign covered, for example, by the snow, or maybe the sign can be covered by another sign, or the sign can be manipulated by a human. So in general, the traffic signs recognition is composed of two steps, a detection and classifications. So detection problem, we scan the image of scene in multi-scale fashion and looks for location of traffic signs on the image. In this stage, the system usually does not distinguish one traffic sign from another. In the classification problem, we determine the type of each traffic sign in the image. So in our case, we will explore the recent success of convolutional neural network for learning features from data. So why we need a self-driving car? So if we take in consideration that more than 37,000 lives were lost on US roads in 2016, or over 40% of fatal crashes involve alcohol, distraction, or fatigue, then yes, self-driving cars can increase safety and assist people with disabilities. We have also from World Health Organization that more than 1 million fatalities in 2015 is due to car accident. So many technology writers believe that in the future, self-driving car will be safer than cars with human drivers. So this is different levels. So level 0 means no automation, and level 4 is fully self-driving automation. And between 1 and 3 is limited self-driving automation. So self-driving car enable people with disabilities to take advantage of this technology. So this is the outline of our project. So in the beginning, we will explore the data we are using. Then we model the architecture of our model. And then we make a training. And after that, we perform some parameters tune-up. And then we test our model on test data and on scene data. Then we conclude. So the data sets considered as the German traffic sign recognition benchmark. So the data set is around 51,000 labeled image and for 3 classes. The data is splitted by 2, the training set around 39,000 and the test set around 12,000 images. For the validation set, we are considering 20% of the training set. So here we show some samples on our data. As we can see, all the images are not in the good quality, and the labels are not balanced. So for the beginning, we start by performing normalization of the inputs images from 0 to 1. And then, as we said before, for the validation, we are taking 20% of the training set. Then we perform the encoding for the output images. But here we make the hot encoding for the labels or the output images. So this is two examples that we show here. This is the output 12 that we can see here, and the output 1. So this is before hot encoding, and this is after hot encoding. So we can see the output vectors. Here we have like 12, and for this one we have 0. So this is, we are listing the sign names. As we can see, this is like for the length of this list is 43. For the software, we are using Anaconda and Jupyter with the Keras API. For my machine, we are using I am using my machine, which is actually Intel i7 with the RAM 16 gig. So this is our first model, or the first architecture we are testing. This is very simple. So we are using 4 layers, 2 conventional and 2 fully connected. So the total parameter is around 75,000, which actually is a very small network. The result shows that the systems converge correctly after few epochs. So here the table summarizes the result. So we reached 99.48% for the training and 98.42% for validation, and then we reached 91.78% for the testing sets. We were also able to improve our test performance by adding some regularization to this network. So this one was simulated for 50 epochs. Then we test a very large and complex network. So the total parameter in this network is around 1 million. And as we can see, we have 2 conventional layers before every pool layer. So this is a good idea for larger and deeper networks because multiple stacked convolutional layers develop more complex features of inputs before pooling operations. We have also a kernel of 5 by 5, and then maximal pooling used is 2 by 2. So the last fully connected layer holds the output. So in our case, the class scores. So the simulation was done with a learning rate of 0.01, and we tested for this one for 20 epochs and a batch size of 128. So as we can see, the total number of parameters is around 1 million, and the table shows the results. So we have much better results than the first network. So we got 99.12% of our training, then 99.70% for validation, and around almost 96% for the test set, which is actually very, very good. So in this graph, we are showing the confusion matrix. As we can see, all the diagonal is holds the maximum numbers, and since our data are not balanced, of course we have maybe some low values in diagonal. In this slide, we are showing the test performance. So as we said before, we reached 96%, and this is how we calculate the test performance. So we got 514 badly predicted among 12,000, which is actually very, very good. So in the next slide, we are trying to do some analysis for these 514 images to see what exactly or why we cannot predict correctly this outputs. So this is like we are showing here three images. So this one is I think is very much simple and very much easier. So we got this is the corresponding probability outputs, and we see for this one and this one, the corresponding probability are very, very close, which means that by changing a little bit some parameters, we can improve for sure our performance. This case is a little bit more complicated, and we can see the probability also are very, very different. In this slide, we tested also some unseen data that we got from the internet. So in this case, we can see the image is road work, and this is exactly what the model predicted. For this one, we have no entry prediction, which is exactly correspond to the input image. This one we'll see also, this is a speed limit 3 kilometers per hour, which is exactly the same image that we have for the input. And the same thing for this image, we have the right of way at the next intersection. So we can see that our model can predict correctly all the input that we got from internet or unseen data. So in conclusion, the simulation result confirm the high efficiency of the convolutional neural network in computer vision. So even with some challenging condition on the input images, the performance was around 96%. But still the biggest challenge for the network is no false positive prediction is allowed. In other words, its positive rate must be 100%. For that, very deep analysis is very necessary. We have also to make another analysis about the badly predicted images, so we can maybe increase the performance of our network. Thank you very much for watching.